The Sun is a fairly ordinary star. There are stars that are much smaller than the Sun, and also stars that are much larger than the Sun. Stars with larger masses than the Sun are also hotter and brighter than the Sun. Brighter stars produce energy at a faster rate than the Sun, which means that they run out of fuel faster. Brighter stars also have a more spectacular death than our Sun. Yes, I said that our own Sun will eventually die. Don't worry though, it won't happen for approximately 5 billion years, and it will be a rather slow and boring death. In case you're still worried about the death of the Sun, let's put 5 billion years into perspective. We often think about the pyramids of Giza as old, but they were built only about 5,000 years ago, within the realm of written history. Earlier still, the oldest archaeological artifacts from North America's first Aboriginal peoples date from 14,000 years ago, which, from an astronomical perspective, is still very recent history compared to the first modern humans, Homo sapiens sapiens, who lived about 200,000 years ago. To put that into perspective, that's about 800 generations of humans, or a time when your great 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 grandfather or grandmother lived. And that's only 200,000 years. We'll need another 25,000 of those to get to 5 billion. Let's jump back 1,000 times further. If we multiply 200,000 years by 1,000, we get 200 million years ago, which is the beginning of the Jurassic Age when dinosaurs roamed the Earth, and plesiosaurs like this one swam in the oceans. This is also close to the time it takes the Sun to make one full orbit around the center of the Milky Way galaxy. That means the Sun celebrates its galactic birthday every 200 million years. If we multiply 200 million years by 10, we get 2 billion years, which is when the Earth's atmosphere first became rich in oxygen, a milestone in the evolution of plants and animals on Earth. The Sun is still older than 2 billion years, though, since the Sun and the Earth were formed close to 5 billion years ago. This means that the Sun isn't even halfway through its life cycle yet, and it still has about 5 billion years to go. It is convenient to classify the main sequence stars into two groups: high-mass stars with mass 8 times the Sun's mass or larger that die in a supernova explosion, and low-mass stars with less than 8 solar masses that have gentle deaths. When a star runs out of hydrogen in its core, it transforms into a red giant star, which is stable for a period of time that is about 1/10 as long as the time period that it is a main sequence star. For instance, the Sun is estimated to have a total lifetime of 10 billion years as a main sequence star and another 1 billion years as a red giant star. During the red giant stage of a star's life, it swells out to a larger size that could be 10 or 100 times larger than it was during the main sequence. When it swells, its surface cools off. So from Wien's law, its color becomes redder, hence the name red giant. The star will expand during the red giant phase. During this phase, its mass stays approximately constant, but its radius becomes larger. The acceleration due to gravity depends on a constant divided by the square of the star's radius. This means that as the star expands, the acceleration due to gravity at the surface of the star becomes smaller. If an astronaut visits the star and floats near the surface of the star, the astronaut will feel a weaker gravitational force towards the star when the star expands. This makes it easier for the astronaut to escape from the star's gravitational pull as they leave. What is true for the astronaut is also true for the gas in the outer layers of a red giant star. As the star expands, the star's outer layers aren't very strongly attracted to the rest of the star. Any small disturbance can end up pushing the outer layers outwards. Eventually, low-mass stars end up as a red giant that sheds its outer layers into a beautiful cloud of gas, confusingly called a planetary nebula. This image is a particular planetary nebula that is commonly called the Ring Nebula. The radius of the nebula is approximately 1 light-year across, which is much larger than the size of the red giant whose outer layers disperse to create the nebula. At the center of the nebula, you can see a bright star. That star is the leftover core of what was once a red giant star, and it's called a white dwarf star. A white dwarf star is a rather peculiar type of star. The strangest thing about a white dwarf is that it can keep its size constant in time without any nuclear fusion keeping it hot. A typical white dwarf has a mass that is about the same as the Sun, but a size that is closer to the size of the Earth. The composition is mainly carbon that has solidified into a crystal structure. The electrons zoom around wildly, creating an outward pressure that balances gravity. The electrons travel around rapidly due to a quantum mechanical effect called degeneracy pressure. Degeneracy pressure is due to the Pauli exclusion principle. That states that particles such as electrons or neutrons are not allowed to exist in exactly the same state. If we were to try to make the particles have exactly the same location with zero speed, they would be identical. In order to keep their identities unique, the particles move quickly with different speeds. As a result, they move around and bounce into each other, creating a gas pressure. This effect does not depend on the temperature. So if a white dwarf cools down, the degeneracy pressure will keep the star a constant size. This means that a white dwarf star could potentially live forever. When we look at planetary nebulae, we always see a white dwarf in the center. Ultraviolet photons emitted by the white dwarf ionize the gas in the nebula, causing it to glow with beautiful colors. Over the course of thousands of years, the gas in the nebula slowly starts to disperse and mix with the other gas in between the stars, and the white dwarf cools. After a few tens of thousands of years, the white dwarf will be isolated and will slowly cool down and fade away. In the early 1900s, astronomers thought that all stars ended up as white dwarfs. That changed in 1930 when a young Indian astrophysicist named Chandrasekhar started thinking about the electron zooming around in a white dwarf star, keeping it from gravitationally collapsing. Chandrasekhar realized that in order to keep a high-mass white dwarf star from collapsing, the electrons would have to travel at faster and faster speeds. If you extrapolate, the prediction is that at some critical stellar mass, the electrons would have to move at speeds faster than light. Chandrasekhar knew that it is impossible for electrons to travel faster than the speed of light. This led him to calculate the largest mass that a white dwarf star can have. This mass is now called the Chandrasekhar mass and is 1.4 times the mass of the Sun. What happens if you try to add extra mass to a stable white dwarf star that has a mass equal to the Chandrasekhar mass? Well, electron degeneracy pressure will not be capable of combating gravity, and the star will collapse. Approximately half of all stars have a binary companion. We will learn later on in Module 5 that if two stars are very close to each other, mass can flow from one star to the other. There are many binary systems where a white dwarf star gains mass from another star. If the added mass makes the white dwarf's mass go over the Chandrasekhar limit, then the white dwarf will implode. This implosion heats the star, allowing the carbon in the star to explosively fuse into heavy elements such as uranium. The explosion destroys the star and sends the heavy elements outwards. This type of explosion is called a Type 1a supernova. After a supernova explosion takes place, there is a hot glowing cloud of gas left over called a supernova remnant. In the year 1572, the Danish astronomer Tycho Brahe observed a bright new star appear in the sky and then fade away. The new star was the supernova explosion. In modern times, when we point a telescope in the part of the sky where Tycho Brahe observed the supernova, we see this glowing and expanding supernova remnant. We now call this supernova remnant Tycho, after Tycho Brahe. This picture might look similar to the picture of the Ring Nebula that we showed earlier, but the Ring Nebula is smooth, while Tycho is very lumpy. This is evidence that the process that formed the Ring Nebula was gentle, while the formation of Tycho was violent. In addition, Tycho is emitting X-rays, while the ring mainly emits visible and ultraviolet light. The point sources of light are foreground stars that are located between us and Tycho. There does not appear to be any stellar core left over after this supernova. It is probably true that all Type 1a supernovas do not leave behind any remnant star. Could our Sun die in a supernova explosion? The Sun will eventually transform into a white dwarf star, but since the Sun does not have a binary companion star, it will not be in any danger of gaining so much weight that it explodes.